Hello class, this is going to be our flipped classroom on thermochemistry. As usual, if you get to a point where you need to stop, please do so, pause and take some notes. Now first let's get some definitions out of the way. The definition of thermochemistry is simply the study of heat in chemical reactions. Now when we say heat, we can refer to it in two ways. A reaction could either be exothermic, which means heat will ultimately be released in the reaction, or it could be endothermic, which means heat would be absorbed in the reaction. Another term we need to discuss is the term delta H. Now delta H is the symbol for the change in heat. It could also, however, be called the heat of a reaction, since when you start with a reaction, all the reactants have some amount of energy, and so do the products. And finally, the term enthalpy, E-N-T-H-A-L-P-Y, also means heat of reaction or change in heat, or delta H. Now, how do we calculate the heat of a reaction? Well, the formula for delta H is you take the heat of the products minus the heat of the reactants. So you subtract heat of products minus heat of reactants. Or another way to look at it, delta H is equal to heat of products minus heat reactants. So let's give an example. Let's say that I had products that had a heat of 100 kilojoules and I had reactants at a heat of 20 kilojoules. So if I do 100 minus 20, I get 80 kilojoules. However, I could also have a situation where the delta H is negative. Let's say the heat of the products was 50 kilojoules and the heat of the reactants was 90 kilojoules. So if you do 50 minus 90, you get negative 40 kilojoules. So you can see the delta H could either be a positive number or a negative number. But we'll get to that a little bit later and why that is so important. For now, what I want to show you is something called a potential energy diagram. This is found in your workbook. Let's go over what a potential energy diagram looks like. If you notice, I have an X and Y axis, and on the Y axis I've simply written potential energy. I didn't put any units in here, but the units are usually going to be kilojoules. The bottom axis, the x-axis, I've just listed as reaction. So what I'm saying is there's a reaction that's going from point A to point B. It's going forward. You're starting here with reactants, and then you're ending here with products. And this tells you the energies of the reactants and the products. So I haven't actually labeled this with any numbers, but you can make up your own numbers. For example, you could make this energy of 50, you could make this energy of 30. You can put in any numbers you want to show you how this works. So I want to show you what each part of this diagram represents. First, I've called this an exothermic reaction. Now, how do I know that this particular picture is showing exothermic? Well, remember, exothermic means heat's released, right? I don't have numbers here for reactants and products, but clearly the reactants have more energy than the products. What this means is that after the reaction is over, there is less energy. Now, if there's less energy, you've lost some of that energy. That must mean the energy was released. If it was an endothermic reaction, the products here would be higher than the reactants, which means it absorbed energy. Now you notice that I have all these different lines here. Let me explain what each line represents. The first line should be pretty obvious. Since this is the reactants, this line here represents the energy of the reactants. We'll call this the potential energy of the reactants. And down here, I have a little key. Arrow 1 is the potential energy of the reactants. Notice the reactants are always going to be on the left side, because we always start writing reactions from left to right. Next, I want to talk about arrow number 2. Arrow number 2 starts at the bottom here and goes all the way up to the product line. So no surprise, arrow 2 represents the potential energy of the products. And again, as we said earlier, in this example, the products have less energy than the reactants. Next line I want to talk about is line number 3. So line number 3, notice it starts where the reactants begin, right here. It's not starting at 0, it's starting here. And it goes all the way up to the top of this curve. This is called the forward activation energy. Now, why is it called the forward activation energy? Well, think about what this arrow is representing. We're starting here with some energy already because the reactants have energy, and I'm putting in more energy to get to the top of this curve right here. Well, that's the energy I need to start or initiate the reaction. So that's why it's called the activation energy. And it's specifically called the forward activation energy because it's the energy needed to take the reaction forward. There is, however, another line, line number 4, which starts at the products and again goes up to this point here. This is called the reverse activation energy. And if you think about it, it makes perfect sense because this would be the energy needed to start at the end and go backward, to go back to where you started. So that's the energy you need to go backward. The most important line, however, is this line right here, line number 5. And notice it's the difference between the products and the reactants. That's why I drew some lines here in between to show the difference between product energy and reactant energy. And if you remember, we already discussed what that is. The difference between the products and the reactants, or heat of products minus heat of reactants, that is the change in energy, or the enthalpy, or the heat of reaction, symbolized by delta H, which I have right here. You might also notice they have a little symbol right after delta H. I'm going to bring that up close. Delta H RXN. RXN is shorthand for reaction. So delta H is heat of reaction. So you can call it heat of reaction or delta H or enthalpy, whatever you like. They all mean the same thing. The last arrow I want to introduce you to is arrow number 6, which starts all the way at the bottom here and goes all the way to the top of this curve. That is called the activated complex. It's not the most useful bit of information because all it tells me is the amount of energy that this point has, but I really don't care about the energy of the entire line because I'm not ever starting at 0. Notice I'm either starting here with reactants or starting here with products. It just gives me the total amount of energy. Now, I want to use this to solve some questions. So let me show you some questions there on the next page and see if this makes sense to you. So we're going to go back and forth between this picture and the next page. On the next page it says, if the energy of reactants is 25 kilocalories per mole and the energy of the products is 10 kilocalories per mole, what is the heat of the reaction? Now at first you may look at this and go, I don't even know what this is asking. How am I supposed to know the heat of the reaction just from this information? Well, let's use this in conjunction with the picture. I just told you 2 bits of information. That the reactants have an energy of 25 and the products have an energy of 10. Let's use that in this picture. I just said the reactants have 25 units of energy, except I'm changing it from kilojoules to kilocalories per mole. It doesn't matter. I'm just going to put the number 25 right here. That's the units of energy that the reactants have. I said the products had an energy of 10, so right here we'll call that 10. So then my question again is, what is the heat of this reaction? And remember, to calculate heat of reaction, or delta H of reaction, you simply have to do heat of products, remember the products come first, minus heat of reactants. Well, if the products have energy of 10, and the reactants have energy of 25, then 10 minus 25 is negative 15, so therefore, the delta H is negative 15 kilocalories per mole. Notice it's a negative number, which is a dead giveaway that this is an exothermic reaction. Anytime you get a negative value for delta H, that means energy is released. Negative delta H means exothermic. You might want to make a note of that. Now the next question. From the information we just got from question 1, and given that the heat of the forward reaction is 45 kilocalories per mole, what would be the heat of the reverse reaction? Now again, on paper with just these words here, it might seem a little confusing. Let's go back to the picture. I already have all this information here. I have that this has 10 units of energy, this has 25 units of energy, and I'm now giving you that the forward reaction is 45 units of energy. Now what is the forward reaction? Again, that would be line number 3. So from here to here is 45 kilocalories. The question is, what is the heat of the reverse reaction, which is arrow number 4? So I want this line, right? Well, think about it. From here to here, we've already established that's 15 units of energy. It goes from this point to this point, from the product line to the reactant line is already 15. Now technically it's negative 15, but that's because we're going the other direction. If we're going up, that's 15. So if this is 15 and this is 45, then this, if you notice, is 15 plus 45. That would be a total of 60 kilocalories per mole. So you'd simply write 15 plus 45 equals 60, and the units are 60 kilocalories per mole. That means it's going to take 60 units of energy to make this reaction go backwards. Notice that the forward activation energy was only 45, but then again, look at the arrows. This arrow is longer than this arrow, so that makes sense. Now finally, the last question is, from questions 1 and 2 that we've just answered, what would be the activated complex for this reaction? How much heat is in that? So in other words, I am looking for this entire line, line number 6. And I can think of 3 different ways to calculate it. I look at line number 6 and say, wait a second, isn't that the same as arrow 1 plus arrow 3? Well, yeah. And if arrow 1 is 25 and arrow 3 is 45, 25 plus 45 is 70. Or I could say, wait a second, isn't it also the same as arrow 2 plus arrow 4? Well, yeah. Well, then arrow 2 is 10 and arrow 4 is 60. 10 plus 60 is also 70. Or if I want to make it really complicated, I could say it's the sum of arrow 2 plus arrow 5 plus arrow 3. All these together add up to this long arrow, right? So 10 plus 15 plus 45 still equals 70. So no matter how you figure it out, you're going to get to be 70 kilocalories per mole. Now I think you can see from here that it's really easy to calculate things like delta H, or heat of forward reaction, or heat of reverse reaction, just by having this graph and by given the numbers. The only thing that makes this complicated is when you're given words without a picture. So what's the obvious thing to do if you see this on a quiz and you're trying to figure out an answer? Draw a picture. You could either draw an exothermic picture, which would look something like this, or if it's an endothermic reaction, it would look something like this. Exothermic, notice the products have less energy than reactants. Endothermic, they have more energy than the reactants. In exothermic, the delta H is going to be a negative number. In endothermic, the delta H is going to be a positive number. Okay? We'll do more of this in class, and that's it for this lesson on thermochemistry and potential energy diagrams.